this lecture we shall be discussing about some of the properties of switching functions and switching expressions, properties of switching functions. Now, recall earlier we talked about the notions of literal, switching functions, switching expressions and so on, and we looked at a number of rules, basic rules using which you can manipulate such switching expressions. Now, since our ultimate target is to design and implement some functions using the basic gates and or not, NAND, etc. So, let us try to move in that direction. So, in this lecture we shall be first introducing some of the basic concepts of switching expressions, and then we shall see how we can use them in designing circuits or functions. Fine. The first thing we talk about is something called Minterm and Maxterm. But before trying to define what Minterm and Maxterm is, let us define a literal. What is a literal? Well, as this definition says, literal is nothing but a variable which can appear in either uncomplemented form or in complemented form. So, suppose I have an expression, let us say a b bar c or a d bar. Now, here examples of literals are this a, b bar, c, a and d bar. There are a total of 5 literals in this expression. Okay? Literal is a single variable either appearing in uncomplemented form or in not complemented form. So, here some examples are given x x bar, y y bar, just like that. Now, let us try to see what is a minterm and a maxterm. Now that we know a literal, consider an n variable switching function f, where the input variables are, let us say x 1 to x n. So, any product term, okay, product term means an AND of some of these literals, well in again complemented or uncomplemented form, because literal definition is that. So, a product term that contains all the n literals, it is called a minterm. Let us consider a function, let us say f of 3 variables a, b and c. In this function, some examples of minterm will be a, b bar, c. Let us say another example will be a, b bar, c bar and so on, a, b, c. So, all the literals should be appearing, all the variables literals for those should be appearing, they are called minterms. Similarly, maxterms refer to the OR operations. So, again for this 3 variable function, if I write some term, let us say a plus b plus c bar, this is a maxterm. Then similarly, a bar plus b bar plus c, this is also a maxterm. Okay? These are the basic definitions. So, some examples are shown here in this slide also. For the 3 variable function f of a b c are the input variables. Some examples of minterms are this. You see, if some of the variable is missing, for example, a b, that will not be a minterm. Okay? A minterm must contain all the variables either in complemented or in uncomplemented form. Similarly, maxterms will refer to the sum of the literals corresponding to all the variables. Okay? These are minterms and maxterms. So, some properties of minterms and maxterms are, well, a minterm will assume the value 1 for exactly one combination of variable, maxterm assumes the value 0 for exactly one combination. Let us see what we mean by this. Take an example, a function of 3 variables a, b, c. let us first look at the so called sum of products expression, where let us say my function is like this a b bar c or a b c bar or a b c. So, according to definition, these are minterms, there are 3 minterms. So, what I say is that a minterm assumes the value 1 for exactly one combination of variables. You consider the first minterm, only when the input variable a is 1, b is 0 and c is 1, the first minterm will be having a value of 1, because a b bar means 0 bar is 1, c is 1, 1 and 1 and 1, it will be 1. Similarly, for the second one we require a equal to 1, b equal to 1 and c equal to 0, and for the third one we require a equal to 1, b equal to 1, c equal to 1. So, for exactly one combination of the input variables, a particular minterm will assume the value of 1. Okay. Similarly, for a maxterm, the condition is slightly different. Again, let us say take a function again of 3 variables. So, I am writing it in terms of maxterms. Let us say one maxterm is a plus b bar plus c and let us say a bar plus b bar plus c bar and let us say a plus b plus c. So, there are 3 maxterms. Now, let us take an example. Let us say if we follow our previous approach, you try to see for which combination this will be 1. You see a, this is the OR function. So, either a 1 or b 0 or c 1. Let us say if a is 1, then the first maxterm will also be 1, because a is there, a or 1 or anything is 1. Similarly, the last one here also a or is there, this will also be 1. So, just by taking a equal to 1 will not serve our purpose. Rather, what we will do, we will see for what combination these minterms will be zeros. See, a or b bar or c, it means that if a is 0, if b is 1 and if c is 0, then all these 3 things literals will be zeros, 0 or 0 or 0, the first maxterm will be 0. Or for the second one, let us say a is 1, b is 1 and also c is 1, and for the third one a is 0 or b is 0 or and c is 0. So, if we have these conditions, this condition says that when this input combination is there, this maxterm will be 0. So, what I can say is that you see this statement now, a maxterm assumes the value 0 for exactly one combination of variables. For this exactly one combination of variable, the first maxterm will be 0. For exactly this combination, second one will be 0, and for this combination, the third one will be 0, right. So, just remember this. Now, this minterms and maxterms can be classified as either true or false. So, I can say some minterms as true minterms and some minterms are false minterms. So, how are they defined? This definition is made with respect to some given values of input variables. For some specified given value of the inputs, if I evaluate the values, some of the minterms will be having the value 1, some of the minterms will be having the value 0. So, accordingly I call them either true minterm or false minterm. Similarly, I can evaluate the maxterms, some of them will be 1, some of them will be 0, and accordingly I call them true maxterms or false maxterms. This is how the definition goes. Let us look at some examples. Let us take a simple switching function here, f of 3 variables x, y, z, x bar y or plus x, y, z. You see, this x, y, z is a minterm, all right, all 3 variables are there, but x bar y is not a minterm. So, what we do? This x bar y I multiply it by z plus z, multiply means AND, because z plus z bar is 1. So, anything AND 1 will be the same thing. So, if I do this, this is nothing but x bar y z or x bar y z bar. So, effectively this x bar y, this product term is corresponding to 2 different minterms, x bar y z and x bar y z bar. This is what is mentioned here, right. Similarly, if you take a product of sum, there are some products sum x plus y, y plus z and product of that, product of sum terms. So, here again these are not max terms because all the variables are not present, let us say x plus y. So, what you can do? You can write it as x plus y plus z z bar, z z bar is 0. So, anything odd 0 is 0. Now, you have this. Now, we apply distributed law. This will be equivalent to x plus y plus z and x plus y plus z bar. Similarly, you can do for the second term. So, in this case the true max term will be x plus y plus z, x plus y plus z bar, and the third one will be coming from y plus z, x bar plus y z. This x y z will be common to both. Okay. This is how you can calculate which min term or max term are true, the remaining ones will be false. Okay. Fine. Now, let us try to take a small real example, and with the help of that example let us see how this concept of min term and max term goes. The example we take is that of a 3-bit adder. Well, we already have learnt earlier how to carry out binary addition. 3-bit adder is sometimes known as full adder. There are 3 inputs A, B and C, and as the output you will be having a sum 1 bit and a carry, that will also be 1 bit. So, let us see how a full adder is defined. As I said, it will be having 3 bits A, B, C as input, it will be having a sum output and a carry output. And here we are showing the truth table of the full adder. So, you see, for all combinations of A, B and C, we have listed what will be the sum and what will be the carry. Okay. So, if you add all zeros, the sum is 0, no carry, 0 and 0. If you add 0, 0 and 1, the sum is 1, but no carry. Similarly, 0, 1, 0 or 1, 0, 0, there is a single 1, sum will be 1, no carry. But if there are 2 ones, 0, 1, 1, 1, 0, 1 or 1, 1, 0, if there are 2 ones, then sum will be 0 and carry will be 1, because carry and sum 1, 0 in decimal means 2. And lastly, if I add 1 and 1, which is 3, 3 means 1, 1 in binary, right. So, sum will be 1, also carry will be 1. Now, you see, this again we shall be coming back later. The way we can just express or write down the expression for this sum and carry are very simple. First, look at the sum. You look at the column for sum, you find out that for which rows the sum is 1. There are 4 such rows. Then you look at the corresponding input combinations. These are the corresponding input combinations for which the sum will be 1. Okay. So, if it is 0, you use that variable in complemented form A bar. If it is 1, you use it in uncomplemented form C. That is, your first row says 0 0 1. So, you write A bar B bar C. Second one says 0 1 0 A bar B C bar, 1 0 0 A B bar C, and finally 1 1 1 A B C. Right? This is how you can write down the expression for this sum, switching expression, directly from the truth table. This is very simple, right? You see which are the ones and then write down. We shall again be coming back to this later, as I said. Okay. Now, let us come to the carry. Look at the carry function again. For the carry also, you see there are 4 ones, 1, 2, 3 and 4. So, if you follow that same principle, what will be the expression? 0 is 0 1 1. So, it is A bar B C plus second one is 1 0 1 A B bar C plus third one is 1 1 0 A B C bar and 1 1 1 plus A B C. So, I took the same example earlier once. This A B C I am writing as A B C or A B C or A B C. I can write like this. There is a rule of switching algebra which allows me to write something as same thing plus same thing, and I combine A B C, A bar B C with the first one, this with this and this with this. You see A bar B C and A B C, if I take B C common, it becomes A or A bar, A from here and A bar from here. From the second two, if I take A C common, I get B from here and B bar from here, and lastly from this and this, if I take A B common, I get C plus C bar. Now, A plus A bar is 1, B plus B bar is 1, C plus C bar is 1. So, I get finally A B or B C or C A. So, what I am showing here is the same function, but in a minimized form, A B or B C or C A. Okay? This is what a full adder is. So, talking about the true minterms for this sum, there are 4. So, the true minterms will be these 4 corresponding to the rows where sum is 1. Similarly, for the carry function, the 4 true minterms will be 0 1 1, 1 0 1, 1 1 0 and 1 1 1, that corresponds to this. So, in a similar way you can just find out the max terms. Okay. Say for the 1, max term will be A bar plus B bar plus C. Second one, it will be A bar plus B plus C bar. This one will be A plus B bar plus C bar and so on. Okay. Fine. Now, let us introduce some more definitions. There is something called a unate function. You see, it means we had defined what is a switching expression. We talked about literals. Literal is a variable which can appear in complemented form, also in uncomplemented form. We say a function is unate if for every variable, let us say for a variable A, well A means A will appear only in complemented form or in uncomplemented form, not in both. That will be called a unate function. So, let us see the definition. A switching function is called unate if no variable appears in both complemented and uncomplemented form. Just you note this term, minimized expression. Well, I will take some examples. Suppose a switching function A B plus B D, this is unate because everything appears in uncomplemented form. Take another example, A B bar plus B bar D, this is also unate. Let us take another term, let us say A D. So, A appears in uncomplemented form, B appears only in complemented form, D appears only in uncomplemented form, this is also unate. Now, you consider an function like this a b c bar or a b c. Now, you may say that well this is not unate because c is appearing in both complemented and uncomplemented form, but I will argue that this expression is not minimized. So, if I take a b common, there will be c bar or c and c will cancel out, this is equal to 1. So, this will be only a b and a b is unate, right. So, this minimized this term is important. There are two special categories of unit function. So, I say a function is called positive unit if all variables appear in only uncomplemented form, there is no complemented literals. Similarly, I can define negative unit if all variables appear in only this will be complemented, sorry, there is a typography, this should be complemented. So, if it appears only in complemented form, then it is called negative unit, right. And if it is not unate, then it is called non-unate. So, for the full adder function, the carry is a positive unit if you can check a b or b c or c a, but for sum the variables appear in both complemented and uncomplemented form, that will be non-unate. Okay. Fine. Now, let us talk about some unique way of representing functions. You see, we said that a function or a switching function is given to you, you can apply the rules to carry out minimization. Now, minimization can be carried out in a number of ways. Well, I mean, if we can figure out which rule to apply, maybe we are able to minimize it very well, but it may also be possible that we have minimized it to some extent, but then we have missed out some rules. So, we have a reduced expression, but that may not be the smallest possible expression. Okay. So, there is a question, is it possible to have some kind of a unique representation of a function? Well, any unique representation is sometimes called canonical representation. So, we are talking about canonical representations of functions. Let us see that. Canonical representation of switching function, canonical forms. Now, as I said, canonical form is nothing but some unique way of representing a function. Given a truth table, from the truth table we can directly arrive at two different canonical forms. One is called canonical sum of products, which is sometimes also known as disjunctive normal form, or as a product of sum terms, which is called conjunctive normal form. You see, normal form is a term which is used in propositional calculus, which refers to some kind of canonical representation, some kind of a unique form of representation. Okay. Let us first look at canonical sum of product. So, what you are saying is that you have the truth table. From the truth table, you identify all the true minterms. True minterm means the rows for which the output is 1. Take the sum of all the minterms. So, this we have already showed an example earlier for the full adder. For the full adder, sum will be like this and carry will be like this. You take all the corresponding rows for which the sum is 1, there are 4, carry is 1, there are 4. Now, what we are saying that this is nothing but the canonical representation. You see, I mentioned that this carry function can be minimized, but here we are not minimizing. If we are not minimizing, from the truth table we have seen that there are 4 ones in the sum and there are 4 ones in the carry. So, if I list out all the 4 like this, this will obviously be a unique representation. There is only 4, it is not 3 or 5, there will only be 4 such minterms, right. So, if I express a function as a sum of the minterms, the true minterms, then it will obviously be a unique representation. Now, we can write such canonical expression in a short form as a minterm using the sigma or summation notation. Well, I will explain it to the help of the truth table, that how it is written. Let us take this. Let us consider again this truth table for the full adder. What we do is, for every row of the input, I write down the decimal equivalent of the input. 0 0 0 is 0, 0 0 1 is 1, 0 1 0 is 2, 0 1 1 3, 1 0 0 is 4, 1 0 1 is 5, 1 1 0, 1 1 1, 0 to 7. For this sum, you list out which rows are 1. It is 1, 2, 4 and 7. So, I write it like this: summation or sigma notation. Sigma means sum 1, 2, 4, 7. Similarly, carry 3, 5, 6, 7. Carry is 3, 5, 6, 7. So, this is a compact way of representation of canonical summer products. This 1, 2, 4, 7 or 3, 5, 6, 7, they all represent nothing but some minterms of the function. They represent one row of the truth table, right. This is one way in which you can represent. Similarly, we can have canonical product of sum form. So, what is the rule here again? Rules are very similar. The only difference is you identify the false minterms. Earlier we had identified the true minterms. You find out the rows for which the outputs are 0. Okay, false minterm means this will be 0, not 1, 0, right. Then for every false minterm, you form a sum term, but now the sum term are reversed in polarity. That means, if it is 0 in the truth table, you use it in uncomplemented form. If it is 1, we use it in complemented form. I will take an example of the full adder and explain, right. So, the expression for the full adder are shown. Let me go to the next slide, show the example and then again come back. So, the truth table is shown here, right. So, what we are saying is like this: suppose I want to write down the expression for sum. I want to write down the expression for sum. So, what I do here is that here I look at the false max terms and we see it is 0 0 0. If it is 0, I use it in uncomplemented form. So, here it will be a plus b plus c. Second term 0 1 1, it will be a or b bar or c bar, and third one is 1 0 1, a, b bar or c, and lastly 1 1 1, it will be a bar plus b bar or c bar. So, what does this actually mean? You see, here we are talking about the false minterms, right. But when we false minterm means what? That when a bar, b bar, c bar, this condition is true, a is 0, b is 0, c is 0, then sum is 1. But if either a is 1 or b is 1 or c is 1, like I write it like this, then this will be 1, right. So, it is not a bar, b bar, c bar. See, just apply De Morgan's law, a bar, b bar, c are not of that, is nothing but a or b or c. So, we are actually applying the reverse. 0 0 0 is 0 means not 0 0 0 is 1, not 0 1 1 is 1, not 101 1, not 111 is 1. So, this and this and this and this will represent my function sum. Similarly, for the carry, so I can do the same thing. So, if you go back to the previous slide, so here we have written down the expression for the sum and also the carry. These are obtained in a very similar way. Sum I have shown. So, you can see that the carry also can be obtained. Now, again when you write this down again from the truth table, in a short form you can write it in this way in a product notation using the pi notation. So, again by noting down the decimal equivalents. So, let us see from the truth table once again. Here if you again note down the decimal equivalents 2, 3, 4, 5, 6 and 7. So, sum will be 0 for 0, 3, 5 and 7, 6, 0, 3, 5, 6 and carry will be 0 for 0, 1, 2 and 4, 0, 1, 2, 4. So, you see this is a very simple way in which starting from the truth table I can directly write down a sum of product or a product term sum expression which is canonical. Canonical means it consists of either a sum of some min terms or it consists of a product of some max terms. This is, as I said, is called canonical representation. So, now we know that from a function specification in the form of a truth table, how to write down the expression either in sum of product or in product of sum. Later on we shall see how we can manipulate these forms in various different ways. Okay. So, with this we come to the end of this lecture. So, we shall be continuing with our discussion in the next lecture. Thank you.